All right, and we're back. We're going to be talking about section 1.2b, which we would have started in our previous lesson yesterday, talking about functions and their properties. And we finished off the last video and lesson actually trying to figure out where this function was increasing and decreasing, and unfortunately it got a little rushed at the end and I just didn't get a chance to do a good job with it. So I figured we'd start with that example. Get rid of the glare. There we are. So I already have this equation ready to rock and roll, and I already have the graph ready to go. And what I've done here is I've zoomed in a little bit on the graph. That way we could see really what's going on with our features here. And I know I mentioned it in the last video, but I might as well say it again. Things are increasing when our graph has positive slopes. And the way I described this was, imagine you're riding a roller coaster from left to right. So if you started your roller coaster right here and you started going to the right, your coaster would be going up. And that's why we are increasing from negative infinity, because those are the numbers to the far left, all the way up to -1, because at -1 we spike up to infinity. I can't include the value at -1 because we have an infinite discontinuity right there, a vertical asymptote. However, directly to the right of x equals -1, our roller coaster will be going up again. And we go up until we hit this little peak right here at the origin, which is why I stop my increasing interval at 0. And then I said that it decreases everywhere else, but we might as well get a little bit more technical about that, right? So right here at this maximum value at the origin, our roller coaster would begin to fall. Negative slopes, falling down forever, all the way up until the value x equals 1. At x equals 1, we have another infinite discontinuity, so we cannot include x equals 1 in our interval of decreasing. But we can hop back on, we can hop back on this curve way up here, just to the right of x equals 1, and then continue to fall forever to the right. Now I know it looks like it's flattening out. Technically, it never actually hits flat. It'll never hit the x-axis. It'll just approach it for all infinity. And that is why our decreasing interval is that. So there, we've got that straightened out that we didn't get finished up in the last video. Let's move on to our next concept of functions and their properties, talking about boundedness. What does it mean for something to be bounded below? What does it mean to be bounded above, or just bounded in general? It's almost like saying your graph has a floor or a ceiling or both, meaning a value it never goes above, that would be bounded above. A value it never dips below, bounded below. And if you have a floor and a ceiling, we just say that function is bounded. And when I talk about this highest value or lowest value, I'm talking about the y values. So here, which is dangerously similar looking to that curve, we would say that this function is unbounded. And the reason why it is unbounded is because there is not a y value that is its absolute minimum y. This thing will point down forever, covering every single y value down. And it's not bounded above because over here and here, it's pointing up forever. Now, is there a gap of numbers from here to here? Yeah, but that doesn't matter. Boundedness is describing a ceiling or a floor. Now this curve over here, some kind of fourth degree polynomial it looks like, because it does point up forever, it is not bounded above. However, it does have a minimum value that the curve will never dip below. So this red dotted line that I just put there could be considered its floor. So since it's never going to go below that red dotted line, we can say that this curve is bounded below. Using the same logic, this curve, even though it is pointing down forever, so therefore is unbounded below, it does have a maximum. I mean, it hits it twice, but it doesn't matter. It will never go above that red dotted line. So this one is bounded above. And this ridiculous spaghetti mess, we would just say is a bounded curve because it has a ceiling and a floor. So it's just considered bounded. So for these, we're legitimately just going to be checking for boundedness, and you don't need to know what the graph looks like. It does say to use a graphing calculator to identify bounded above, below, or just simply bounded. And if it's neither, or excuse me, none of those three, we'll just say it's unbounded. So we grab handy dandy graphing calculator. We're going to try to avoid the glare. Oh my gosh, look at all those lights. Okay, the best we can do is right there. Let's go to y equals. Clear. We can type this in. 3x squared. Remember, this is your variable button. There's your square. Minus 4. I mentioned this yesterday, but I'm just going to go ahead and say it again. You need to be in the habit of hitting zoom 6, and that's because you don't want to have to wait for this thing to graph on whatever ridiculous grid you were working on before. So zoom 6 takes us back to our standard menu, or standard grid, excuse me. Oh, look, a quadratic. Yeah, really should not have been surprised by that because it's just a 3x squared minus 4. We should have already known, using a little bit of graph theory, that this graph points up. It points up because the front number is positive, and it's quadratic because x squared. So no matter what we did after we typed 3x squared, this thing was going to do this. Now it doesn't matter what value the vertex is at. All we were supposed to do was figure out, does our graph have any kind of boundedness? And, well, yeah, it does. Because it's quadratic, that points up, it clearly has a minimum value at its vertex. So we would say that this is bounded below. All right, now this next curve, if you have no idea what it looks like, well, that doesn't surprise me because neither do I. So let's go ahead and see what's going on. Go to y equals, clear. Going to be working with a stacked fraction, and you can either press alpha y equals and get this shortcut and just hit enter for n over d, or you could hit math, scroll over to this fraction menu, and then again, there's your n over d command. X, down arrow, 1 plus x, and then again that squared button we just saw a second ago. I'm going to hit zoom 6 and wait for this calculator. You see this yellow spinning circle up here? That means the calculator's thinking. And if we had a ridiculously difficult thing for this calculator to graph, it could be thinking for quite a long time. So if you forget to hit zoom 6 and it is trying its best to graph something just absolutely ridiculous on a window that is not useful to you, now you're wasting time on a test waiting for your calculator to stop thinking. So that's why we want to be in the habit of hitting zoom 6. So what do we see? I know that it's squished, but to the far left and the far right, we can see that this graph is just getting really close to the x-axis. Right here, it is dipping down a little bit, and right there it does come up a little bit. But it never goes below that place, and it never goes above that place. And because of that, we can simply say that this curve is bounded, because it does something like this. Hyper exaggerated. There. So this is going to be absolutely bounded. Bounded above. It does have a ceiling. Bounded below. It does have a floor. So simply bounded. Great. Flip them. So a minute ago, I was talking about those maximums and minimums. Those places of maximums and minimum values are actually called extrema. So we can say local, which means in the general region, that's the lowest point around that area, or absolute, meaning, yeah, that is the lowest or the highest point that graph can have. We don't really need to use the terminology of absolute very often because every absolute extrema is also a local extrema. So for the most part, we just stick with local max, local min. There's a lot of fanciness going on in here, but here's what it says. A local maximum is the highest y value in its general vicinity. A local minimum is the lowest y value in the general vicinity. So turn back because we have some curves drawn. We could describe this point right here as a local maximum. This point right here, local minimum, there's another local maximum because it's the top of a bump. There's another local minimum. This one also happens to be the absolute or global minimum, but it is still a local minimum. This curve has a local max here and here, a local min right there. And this spaghetti noodle is just covered up with extrema. So again, we've been told to use a graphing calculator to find all the extrema and the x values where they occur. So that means I have to teach you how to use your technology because figuring out where those x values occur before you know some calculus, it's quite difficult. But TI is here to save us. Whoa, look at all those lights. Okay, let's see. We find a good place. There we go. Y equals. Ooh, so we're going to get to use a new function in our calculator we haven't seen before, and that is an exponent other than 2. We're still going to hit our variable button, but now we need to figure out how to raise this thing to the 4th power. This symbol right here is called a caret. So we say x raised to the, and you notice it went ahead and threw me up there into the exponent position, and I just press 4. Now notice that my little cursor that's blinking is still in the exponent position, but 4 is the entire exponent, so we need to get out of the exponent position by hitting the right arrow. There we go. So we have x to the 4th minus 7x squared plus 6x. Again, zoom 6. Let's see what it does. Holy cow. Okay, we have a problem. There's clearly a minimum down there, but we can't see it. What happened? Well, I have too many y values up here and not enough y values down here, so we're going to have to adjust this window. And you know what? While I'm at it, this is a relatively skinny graph, so I'm going to shave off some of this x-axis. I'm going to take it back to -5 and +5. And for y's, I don't see a reason to go above, I don't know, 5. Well, how far are we going to dip down, though? Going to have to make an educated guess there. So we press window, x minimum, 5. You see there's still a 0 there, so I'm going to hit delete. X max, 5. And the scale of 1 is fine. Y minimum. I don't know, -20 feels good. Let's just see what happens. Y maximum doesn't need to go to 10. Let's just take it to 5. And my scale. So this is a span of 25. I don't like to have to do this. I'm just going to, decimal scales. So I'm just going to say the scale is 5. That's not going to be a whole lot of tick marks. That's going to give me 25 divided by 5 is 5 tick marks. But whatever. Let's hit graph. Bang. See what happens. Okay. So you saw it was educated guess, and we still didn't go down far enough. More than likely 30 is safe, but just to go nuts, I'm going to take it all the way down to -40. I'm just going to go super ham here. From -40 to 5 is 45. That is still divisible by 5. That'll give me 9 tick marks. I'm good with that. Graph. Okay, there we go. That's good enough. That is good enough. I'm going to just quick sketch this thing. Picture not drawn to scale because I'm a math teacher, not an art teacher. And what are we looking for here? We're looking for our extrema, and I'm seeing 3 extreme values. I'm seeing a minimum here and a minimum here. We also have a maximum here. And basically what we've been tasked with here is finding the coordinates of each of those three extreme values. And this calculator will do that for us. If you recall, I taught you how to calculate intersections points. Well, the calculator will also calculate maximums and minimums. And the reason why I'm saying calculate like that is because we need to use the calculate command, which is blue. So it only works if we hit second. So second trace. And we are going to hunt down our minimums first. So we just hit the number 3. Now, once again, this calculator is prompting you. It's asking you, what is left of the point you're looking for? So we're going to track down this minimum value first. So we need to go left of this bump. So I'm just going to hold to the left until it gets to the left of it. And you just need to be a little bit left. It doesn't matter how far, just don't go too far. So yeah, I'm a little bit to the left, hit enter. And then it says, hey, why don't you go to the right of where you want it? And I go, all right, well, I'll just go to the right a little bit. I'll hit enter. And then it says, take a guess. You just need to be between the two dotted lines and hit enter. And what it did is it told me that my minimum value happens when x is negative 2.06-ish. That's its value. So if you say, what is the minimum value? Oh, it's negative 24.06-ish. This is where it happens. This is what it is. So again, the x's are where they occur. The values themselves are always the y's. And to find this minimum, we do the exact same tricks. Second, trace, minimum is the number 3. And it says, hey, why don't you go left of the point you're looking for? So I'm going to hold the right key for a while. That's to the left. That's to the right, hit enter. And then just go somewhere in between them. There we go. About 1.6 with a minimum of negative 1.77. There. And then lastly, the maximum. And the entire process is exactly the same, except for when we go into our second trace menu, we're not going to hit minimum, we're going to hit maximum instead. So press 4. And then watch, rinse, repeat. Go to the left of where you want it to be, go to the right of where you want to be, go in the middle, hit enter. And we find our maximum at 0.46-ish and 1.32-ish. There it is. And it didn't ask, but this value is your absolute minimum value, also known as your global minimum. All right. The last concept that we're going to cover in this video is symmetry. Now, this is something that you should have learned about in Algebra 2. I don't know if they teach in Algebra 1 or not, but I know for a fact you should have learned about it in Algebra 2, symmetry of a function. And we say that functions have two kinds of symmetry. They can either have even symmetry or odd symmetry. Geometrically, even symmetry means the y-axis cuts the graph in half. Algebraically, what that means is plugging in negative x gives you back the original function. And if you can remember back to transformations of Algebra 2, what that means is reflecting over the y-axis does nothing. That's what that says. And anything that does that, you could say is an even function. So you could say that function has even symmetry, or you could say that is an even function. Remember, it means the y-axis cuts it in half. We test for it by plugging in negative x and seeing what happens. And if after we do all the simplifications, we get back our original function, that is an even function. Now, odd symmetry, you would think, since even is symmetric over the y-axis, you would think that even is symmetric over the x-axis, but you can't have a graph that's symmetric over the x-axis because that would violate the vertical line test, so you wouldn't be dealing with a function, would you? No, Odd symmetry, we say, is symmetric around the origin. So geometrically, it looks like cubics and things like that. They're generally centered at the origin, and then they're going to have to go in opposite directions. But what does that mean algebraically? What is the test? Well, plugging in negative x after the simplification would get you back the same thing as if you had just distributed a -1 across your function. So talking transformations, reflecting over the x-axis, excuse me, I said this backwards, reflecting over the y-axis is the same as reflecting over the x-axis. So changing the sign on your x's would give you the exact same result as changing the sign on your y's. So if you reflected this thing left-right, you'd get exactly the same thing as if you had reflected it up-down. That's what it means to be an odd function. Okay, so you need to be able to identify even and odd functions by picture and by algebra. So these three examples right here, and then we call it quits. So tell whether each of the functions is even, odd, or neither. And you go, okay, well, both tests of symmetry involve me plugging in -x. So let's see, for A, we'll do A in green. Let's check f of -x. F of -x. Everywhere there was an x, I'll plug in a -x. And then we'll simplify. Well, last time I checked, squaring a negative number gives me back a positive number. So -x times -x will give you x squared. And you know what? X squared minus 3, that was my original function. So plugging in -x did absolutely nothing. This is an even function. Let's check B. Let's do B in blue. I like that. Blue, B. Coincidence. Well, this one's G, so I'm not going to say f of -x. So let's see what G of -x gives us. Everywhere G had an x, I'm going to open a set of parentheses, and I will substitute in a -x. And let's see what we get. Well, again, squaring -x gives me x squared. Well, check this out. -2 times -x is positive 2x minus 2. Okay, well, that's not the same thing as g of x, and it's also not the same thing as negative g of x, because negative g of x would have distributed a negative sign across the entire polynomial, so it would become -x squared plus 2x plus 2. So since it's not identical, it's not even, and since we didn't just distribute a negative sign across this function, it's not odd, so we would say that this has no symmetry, or you would say neither. That says nether. Goodness, I can't spell. I can Minecraft though. Well, okay, no, neither. That's how you spell neither. Alrighty, last one. I'll do in purple. Place your bets. Let's see what happens when we plug in a -x everywhere where there's an x. See, if we were doing this in class, this would be one of those times where I'm like, oh, let's take a vote. What do you think it's going to be? What are the predictions? And unfortunately, the only person I can ask that right now is my wife. And as usual, she's not paying attention to me anyway. So let's see. Let's see what we get. Cubing a negative number is going to give you back a negative number. So I will have negative x to the third over, well, squaring this negative x is just going to give me back x squared. So I have 4 minus x squared. The top changed sign, but the bottom didn't. See, this one's a little bit trickier to think about. And in order to pull this off, what you have to remember is that for fractions, if you see a negative sign, you could either say the numerator is negative, or you could say the denominator is negative, or you could just scoot the negative sign to the front of it. And that's looking dangerously like negative, and then whatever h of x was. See, this is h of x, and there's the negative sign in front of it. So plugging in a negative x was the same thing as multiplying by -1. Therefore, this one has odd symmetry. Tricky, tricky. And that's going to do it for 1.2b. Next video, 1.2c, will finish up this section. Enjoy.